All right, everybody. In this first lecture, we're going to be talking about some ideas about science and some ideas about biology. We are going to be using the Krogh textbook, by the way. The fifth edition is the best, and you can get that online. I think the website is called Best Booksellers. You can get that online for like $10. So that's what I recommend doing. Some of those details are in the syllabus as well. So this is chapter 1.1, How Does Science Impact the Everyday World? And science is playing an increasingly important role in the lives of everyday Americans. And what I mean by that is if you go back 20 years or so, Americans didn't really use email, cell phones, or the internet. Those things were certainly around at this time, but if you just looked at the day-to-day lives of people in general didn't really use them. And this is kind of exploded onto the scene. So here's a picture of one of the first computers. It kind of resembles a soda machine. You've got all these capacitors plugged in here and all this complicated wiring going on. And this thing was, compared to the computers we have today, incredibly weak, incredibly slow, incredibly small. Now here is somebody using a tablet. And this tablet is much more powerful, much smaller than this machine, and costs a very small fraction of what that machine costs. So the reason that we have these kind of breakthroughs is because of science and the scientific process in general. Along with this increase in technology and technological advancement has come other things as well, such as an increase in life expectancy, which is shown by this chart here. And you can see these are, by and large, all trending up. Even the one in North America is trending up, generally speaking. And the reason that life expectancy is increasing is in large part because of scientific advancement, leading to things like medicine, leading to things like better doctors, better medical practices. Surgeries that can be life-saving. It's an incredibly important thing, and it is because of science that we have this. So despite these increases in technologies that we use every single day, things like computers and cell phones, and despite a marked increase in life expectancy even over the course of the last 50 years, it has been increasing for hundreds of years, pretty much since the advent of agriculture, and fueled by increases in scientific development. But despite all of those things, the average American has a pretty uneven knowledge of science, the scientific process, and how to interpret what it means. So almost 80% of adult Americans who were surveyed knew that the continents were moving around the face of the earth, which is just, kind of a basic geology fact. And of those surveyed, 25% think that the sun goes around the earth. And I'm certainly not trying to insult anyone or anything. If you think that the sun goes around the earth, come talk to me. We can sort that out. But these are problems, right? These are problems. 1 in 4 people think that the sun goes around the earth. So my job then is, at least in part, to help educate you about what science actually is, and we're going to use the lens of biology to start figuring that out. Science is a body of knowledge. It's a collection of unified insights about nature, the evidence for which is an array of facts. It is also more than just this body of knowledge. It is a way of systematically thinking about. So the unified insights of science are known as theories. And theories are these things that are extremely well supported by evidence, that are explaining some aspect of nature. The one that we are going to talk about most is the theory of evolution. So the problem with theories that a lot of non-science people run into, even scientists do this too, is that they think of them as hypotheses, or they use the word theory colloquially to mean a hypothesis. And as we will see in this class, a theory and a hypothesis are two completely different things. So a theory is extremely well supported by many experiments, by a lot of evidence. It's also defined as a way of learning, a process of coming to understand the natural world through observation and the testing of those hypotheses. And like I said, we're going to be discussing the scientific method in a little bit more detail. So the scientific process begins with the observation of some phenomena. You observe something happening in the natural world, and this leads you to develop a question about it, or a question about what might have caused that thing that you're observing to happen. Those questions drive hypotheses, and a hypothesis is basically just some people, like the kind of elementary definition of a hypothesis is a educated guess. It can certainly be thought of that way. I tend to think of it more as a falsifiable statement about a question, or a testable statement about a question. And those hypotheses lead to experiments that you're actually going to take. You're going to test it because it is a testable statement. You're going to run experiments on it, and then you're going to use that to draw a conclusion. Whatever conclusion you come to could be considered, or could be laid back into this observation phase. So any conclusion you come to feeds right back, and the process can begin again. So the example that I kind of like to use, or I kind of like to think of, is that of a toy car. So my nephew brought me this toy car, and he says, Uncle Aaron, my car doesn't work. Okay, so that is our observation. The observation is, okay, the car doesn't work. Well, if you're looking at a toy car, it's not working. What's the first question that would come to your mind? The first question that came to my mind was, well, are the batteries dead? Did the batteries just happen to die in this car? And so then the hypothesis becomes, well, if we get new batteries, or if we change the batteries, the car should start working again. So you take the car, you put new batteries in it, and you run your experiment. You turn the car on, you push forward on the little RC remote control, and the car moves forward. So the conclusion that you can draw from that is, yeah, okay, the batteries were dead. Or alternatively, if the car doesn't work, your conclusion would be, okay, well, it isn't the batteries that are broken, and this feeds right back into the process of observation. Okay, the car still doesn't work, but we have a new piece of data, and that it's not the batteries. And you can formulate a new question, like, I don't know, maybe the motor is broken or something, and you continue going through the scientific process. But this is the basics of it: observation, question, hypothesis, experiment, and conclusion. And different people have different permutations of this. Some people say that conclusion continues on to things like data analysis or whatever. But this is kind of a nice basic form of the scientific method that we probably, as a person living in the United States, you're probably using this process somewhat regularly, whether you know it or not. So, as I just described, science works through this process of the scientific method, in which an observation leads you to the formulation of a question, which leads to a hypothesis, which leads to an experiment, which leads then to conclusions, which can lead back to more observations and more questions. And science is it's tentative, a testable explanation that has not been proven true. The hypothesis may be tested through a series of experiments as aided by statistical procedures, but science typically does not traffic in truth. We don't really talk about truth very often. We talk more about statistical significance. We talk about causes and effects. And we don't really talk about proof as much. Sometimes you'll see things that are sort of touted as proof, or things that are talked about as though they have been proven, and some things certainly have been. But generally, science does not talk about total proof. It is a tentative explanation of things. And science can always change. If someone brings in new evidence, if someone has done more experiments to prove an old way of thinking wrong, science is adaptable. Science is flexible. The body of knowledge will change to reflect these new findings. So a fantastic example of the scientific method in action is Louis Pasteur's experiment regarding the spontaneous generation of life. So if you take and you eat something, or you eat half of something and you leave it on the counter for a few days, what's going to happen to it? Well, it's going to start to rot eventually. And what's causing this rot is microorganisms. Things are coming and eating the food that you're leaving out, and causing it to decay and start to stink. And so the question then was, for Louis Pasteur, where do these things come from? Or I guess the question is, do these things just randomly, spontaneously generate themselves in areas where they have food to eat? So Louis Pasteur, this is about 150 years ago or so, but Louis Pasteur has access to microscopes because of people like von Leeuwenhoek, who predated him. They knew that there were microorganisms on these food. They knew that this stuff was there. They just didn't know how it got there. So what Pasteur did, a sterile flask, and you put some broth in it. Broth is basically stuff that just microorganisms like to eat. If you take a flask and you fill it with broth, and then you boil the broth to kill anything that may have been in there before, and you just let it sit there and grow, stuff will start growing inside the flask. And so hypothesis one is that living material is generated from non-living material, and that those microorganisms spontaneously generate inside the flask. The second hypothesis is that living material is coming in from outside, and that's why stuff is growing inside this broth. And so what Louis Pasteur did is he wound up doing this thing with this, with a flask. I think they called it a swan neck flask. And what they did, or what he did, was he took and put broth into this flask and he boiled it. He put broth into this flask and he boiled it so that nothing was there, and nothing was able to grow inside the broth. Nothing was able to grow in there. And what was happening was, nothing was able to grow in there because when you do the experiment like this, things just kind of fall in to the broth. But when you have this neck to stop things from coming into the flask, nothing is able to grow. If you then take your flask with this neck on it where nothing is growing, and you remove the trap, or you mix it so that stuff that maybe was caught in the neck is able to get in, then things begin to grow. So Pasteur's observation was that microbes are growing in materials that are sort of left out. His hypotheses, he had two of them, were that maybe things were spontaneously generating, or maybe the living material was coming in from the outside. His experiment to test that was to use these flasks with these necks, and his ultimate conclusion was that indeed nothing was able to get into these flasks, and nothing was able to grow. Clearly there is no spontaneous generation here, and when you keep the outside environment out of the flask, nothing grows. He kind of extended this by making sure that the broth was able to have stuff grow in the flask by removing the swan neck, or the bend, and also by mixing stuff in. But this is a fantastic example of the scientific process at work. So every assertion regarding the natural world is subject to challenge and revision. So anytime you say something in science, like X causes Y, that is open to scrutiny, that is open to a process called peer review. And peer review is what we use to try to make sure that any scientific conclusion we come to is actually a true one. And if you make a scientific claim and it is not true, there are a whole bunch of scientists all lined up to prove you wrong. And that is the very basics of the process of peer review. It keeps the scientific process true, so that if you make a false claim, it is shot down. And it keeps other scientists informed about work that people are doing. So if you're working on a particular organism, odds are really good someone else is going to see it. They're going to check your work and make sure that you've got all of your I's dotted and your T's crossed. And so in this way, science keeps itself true, and it keeps it so that people are readily informed of others' work as well. So I've talked a bit about hypothesis and the scientific method, and I wanted to talk about, when is a theory proven? When can you say with certainty that a theory is 100% true? Well, scientific claims are falsifiable, and that means that they're open to being negated. If you make a claim that seems like it's great on one day, you might get some new evidence later on that proves that statement is not true. And so scientific inquiry is limited to investigating natural explanations for natural phenomena, and kind of when a scientific theory is true is perhaps open to interpretation. Is it when most scientists accept it? Is it when nobody says that it's not true? Because that's an impossible standard. You will always have people, no matter how much proof you have of something, saying that something is not true. And so when a scientific theory is proven is kind of open to interpretation. And these things aren't, like I was saying earlier, they aren't necessarily meant to be measures of proof. They aren't meant to be 100% accurate all the time. They're just giving you explanations about how natural systems work. So moving from science, we're going to narrow our scope down a little bit to the nature of biology. Sort of what is biology and why do we study it?